Good morning, and thank you for joining us today for our event, Improving the Performance of Your Pressure Controller Calibrator. Our presenter today is Tim Francis. Tim is our product manager for pressure and flow calibration products at Fluke Calibration. Tim has more than 10 years experience in precision pressure calibration. We've started here. I'd like to go over a couple of housekeeping points. Please use the chat or Q&A features of WebEx to send questions. Please address both the host and presenter, so both Tim and I receive your questions. We will address most of the questions at the end of the event, so please be patient as we complete the presentation and move on to Q&A. With that, I'll hand over to Tim.
And thank you for joining us. We appreciate your time. We're going to be talking about improving the performance or really getting the most out of your pressure controller. Agenda here. We'll the sense of what we're discussing today. So describe what is a pressure controller for today's discussion. Considerations that in mind using a pressure controller calibrator. And it goes into three groups. First are the mechanical considerations, how you instrument up, the physical setup. Those are considerations. Config setting within the instrument, as well as use with external software. Next considerations. These instruments need calibrated. How does that calibration affect performance and affect your usage of the instrument? And with a discussion on the benefits of new versus old equipment. To each, where does it make the most sense? Take advantage of those. The scope. What is a pressure controller? Talking about here. Referring to here are devices that automatically control and maintain a given hydrostatic pressure. Now, meaning two things. One, hydro being that it's a fluid, so pressure where the media is a fluid, be it a gas or a liquid, and where the goal is a stable pressure that we're trying to measure. Out be situations where it's a dynamic pressure, where we're looking at the freak pressure or things like that, but here we're looking at strictly just the method of a constant pressure, relatively constant pressure, a fluid, a liquid gas. Main categories when we look at these. First, the lower pressure pneumatic controllers. Pneumatic being used as the media. And I'm dividing that as saying where the hills less than or equal to 3,000 psi. Some overlap here with the next group, which is what we think of high pressure pneumatic, and then we have full scales greater than or equal to 3,000 psi, and see it as high as 15,000 psi. Low pneumatic, less than or 3,000 psi, are common and have most applications out in the world. The pneumatic come into play when is very big concern. Automated system. But because working with high pressure gas, there's some inherent challenges that have to be considered. So for many times when working with high pressure, we'll move hydraulic controller at high pressure, and these are pressures up to 40,000 psi. So in our break-off points, lower pressure pneumatic, making the biggest population is 20 megapascal or 200 bar, 3,000 psi and below. The high pressure pneumatic is greater than 3,000 psi, 20 pascal, 200 bar, as high as 15,000 psi. And the high pressures are up to 2,000 psi, or about 280 megapascal. We're going to focus our conversation on the Fluke calibration pressure controllers. Doing that because we're going to advertise the products or anything, but simply this is where we're going to be able to provide the most knowledge is available to us. The reality is that much of what we cover is appropriate for other controllers as well, other manufacturers or older products. So with the products as are covered on the pneumatic, we've got the Brace 6270A microcontroller, P4, and the 7250 series, include things like the 7252 dual channel controller. High pressure pneumatic, there's the PCHG and 7050, and for hydraulic is the PCH and 7615. Of what our discussion is today, let's get into the details, and we'll talk about mechanical considerations. These include things like supply pressure, have your test port configured on your test port, and all things like contamination. When situations where they're not getting optimal pressure control out of their controller, it can usually solved by looking at one out three things, and it's these things exactly here. Either improper supply pressure, too much volume, or a leak on the test port, or contamination causing improper performance from the instrument. So let's apply pressure. That is coming into the instrument that controller is then metering to controlled test pressure. This can have a direct impact on control performance. First, to also make sure they're using clean, dry gas, the pneumatic controllers. Press gas that has not been sufficiently dried and cleaned, that can be an instrument. And air, it'll generate moisture or water in the fluid, in the media, will cause possibly corrosion or even mess. So always best to make sure that you're using clean, dry air or nitrogen gas media. Be a gas bottle. In most regions, it's a relatively straightforward. So it can be easily provided by your local gas bottle provider. You'll need a regulated supply. A self-venting regulator is preferable. Have continuous flow. Conscious of using small diameter tubing or low flow regulators. This really play when you're trying to control into a large volume. If you think about it, you'll have some sort of gas supply, go in pressure controller to then feed and fill large volume. The flow of gas going to your controller, that's going to limit the flow of gas coming out of your controller. That's going to reduce or that's going to increase your time to set point. There's issues there. conscious of using small diameter tubing or low flow regulators going into the supply of your instrument. Supply pressure and how much pressure is required. Different controllers have different requirements. So look at the different pneumatic controllers from Fluke and supply pressures are required on each of those, as they're somewhat representative of the different that are available. PPC4. The is equal to the maximum PPC4 control pressure plus 10%. Normally, the full scale of the instrument, but have the advantage of if full scale of the instrument is say 2,000 psi, but the work you need to do today is only lower pressures, then if you're 10% greater or greater than the pressure that you're going to be working at that time, then okay. That for very low pressure ranges, so the BD15K is 15 kPa gauge, CSI 2. CSI. So if you're using the very low ranges, you apply pressure of about 10 psi or 70 kPa to give you a little bit more of a buffer there. This is pretty useful in the setup, and that it means you don't have to try to find a regulator that will regulate down to 2 psi. Instead, have the advantage of its 10 psi. So is normally going to be the full scale plus 10%, but in low gas pressure sources can be used. But see the maximum desired test output pressure by 10 to 20%. So you need 100 psi on your 1,000 psi device. It's okay to set your supply pressure to as low as 120 psi to get that output. The 7250 family and 7252, 7250 LP, 7250I, and XI, and so forth. A little bit different of supply pressure requirement. The recommended supply pressure is really between 10 and 115% of full scale, or plus 100 kPa, 15 psi, whichever is greater. This is if the full scale of your instrument is 100 psi, then 100 psi supply pressure. If the level of your instrument is 15 psi, then it would be a 30 psi supply pressure. And if it's 1,000, then you set it around 1,100, 1,150 psi. And the best performance with supply pressure. There is in the instrument called supply pressure correction. You're using the instrument with lower supply pressure. Setting that, it will allow the control algorithm to adjust for the lower supply pressure. Depends on how well it can adjust. It does not actively measure the supply pressure, so it adjusts extremely well lower supply pressures. So the best performance with the full scale plus 15 or 50 psi. If you're having control issues, one places to look is to make sure that your supply pressure hasn't drained lower than that. Is the 6270A. Its supply pressure requirement is similar to the 7250, but a little bit different. Recommended is 115% of full scale, or full plus 100 kPa, whichever is greater. That looks the same as the 7250, but it does offer usage with lower or higher full scale pressures, and an onboard sensor to measure the supply pressure and adjust the control algorithm accordingly. Now, it's like the PPC4, supply pressure greater than the highest pressure that you want to go to. Others do not have a built-in pump or compressor or anything where they can generate pressures higher than what's given to them. There's some metering in the pressure that's given. They need to provide a supply pressure greater than the pressure that you're looking to go to. reduced, the active range is less than 10% of the full scale. This is the best control performance overall at the lower pressures. What we mean here is that if your full instrument is 3,000 psi, if your 3,000 psi range or 1,000 psi range, you get your supply pressure at 3,300 psi. In a 100 psi range or a 300 psi range, then you reduce that supply pressure to say 330 psi, signal performance at those lower pressures. To the test port. This is the output of the controller. So it receives supply pressure from our regulated nitrogen bottle with the different valves and so forth. Inside the instrument, it's regulating that pressure, sending it out to the test port. And this you have a controlled, steady pressure on that test port. It's very important to look at how you have the test port configured and how you have items connected to the test port. You just plug the back of the test port. If you put volume on it whatsoever, perhaps just testing out the performance of the instrument, just received the instrument, you just want to play around with it, but you're not to actually calibrate anything yet. That can lead to overshoot. You can expect that there's going to be some level of volume on the input, and if that volume is not there, then rate pressure too quickly. Volume in set times, and it leads to potential other issues. So a large volume that we've got to fill full gas. And so that could take time, especially if flow of our supply gas is limited. And that will be times than perhaps the published specification. Another consideration on volume is that it's preferred to be a relatively constant in volume. Or what's here is that if a scenario where you have a valve in the part of the instrument that close valve and decrease volume, perhaps where it's just the per line, open the valve and now a large volume is filled. And the algorithm in the controller set up to adjusting upon the volume that it's filling. Basically, it's always actively determining is on the test port. Start your pressurization with the valve closed and it sees a small volume. Then in one fashion. If valve on it, that will potentially interrupt the algorithm. The working that has in reverse. If you start the excursion with the valve open, it goes, okay, I have a really large volume here. I can meter very quickly. I've got a large volume to fill. I'm less likely to overshoot. Halfway through, you go, oh, whoops, I don't want to pressurize all that. You close. It's very quickly. You're letting in pressure quite a bit, and now you have the potential of over the target and damaging the instrument. So to have a constant volume relatively on the test port of flow restrictions, especially diameter tubing, going into a large volume on your test port, as you potential sort of we'll see the small tubing, small volume, but in reality, it's trying to fill a large volume on the very end. This results in measurement errors when combined with a leak. One is minimum of 1/8" internal diameter tubing used on the test port between the control and the unit under test. We suggest you be cautious of valves, filters, or excessive fittings between the controller and the unit under test. Matter. As I said, being less ideal control performance, it's tied to the things that we talked about so far: supply pressure, testing, or leaks on the test port. So why does this matter? Well, the gas law tells that pressure is impacted by three things that results in change in pressure. PC, R, but V being changes in volume, T changes in temperature, or number of molecules. With the pressure controller is to have a nice stable pressure. So it's all working to combat the changes in any of these variables, in the volume of the system, in the temperature of the system, or in the molecules. A change is the number of molecules. Will make the system less stable. How pressure controllers can overcome a leak of magnitude. It's large magnitudes. But control is always going to be better without the leak in the system. Let's look at, can a leak cause a measurement error? Let's for measuring flow. A liquid is flowing through a pipe. Flow restriction is placed in the pipe. With pressure on each side of the flow restriction. From the amount of flow of the magnitude of the pressure differential. In other words, they have a faster flow, then we get a larger pressure differential. It's a very common method for measuring flow. You get liquid flow. This sort of situation can with a pressure controller. Near the unit test, then that puts a flow from the controller to the leak. So feed that leak in order to keep stable pressure. We'll have to continue to allow in gas supply pressure. It's going to flow through the system and out the leak on the other end. We're going to have a constant flow of fluid, of gas. If flow restriction between the controller and the unit under test, we could differential. And that means a different pressure at our controller, at our standard, and test. This can be bad. The magnitude is in order to have an impact on your measurement, perhaps getting a very precise measurement, we'll have a very component in the system it is partially closed over a very long period, or a clogged filter, and efficient leak to flow so great of a leak that the pressure controller can't control the pressure at all. It can't happen. So the solution is to also check for leaks, possible leaks from the system. Start your calibration process off with a leak where you take the unit up to allow pressure for a bit to eliminate the temperature effects, and look for a pressure drop. A temperature drop will signify a leak looking for leaks, so people think it's inefficient, a whole lot more efficient than getting through your process and perhaps not being able to generate a pressure because it's too great and having to start over, or performing your calibration, finding it's out of tolerance. And the reason that it's out of tolerance is not because the gauge is bad, but you had a leak in the system causing a pressure differential. Look at contamination. What do I mean by contamination? Looking at liquids or particles in the media. Perhaps on a liquid hydraulic system, we'll be looking at, once again, liquids, but liquid different from what our media should be. We have a water system, and we have with oil in it, that would be contamination and possibly causing a problem. But look at the gas systems, then sort of liquid or part of media can cause problems. They can like clogged valves, which will lead to control issues. They potential measurement errors. Where you have a head height because of a column of liquid in the system that you're accounting for. Also damage the units under test or damage our pressure controller and its sensor. So contamination can cause quite problems. Where do they come? There are different sources to consider. The top three would be these: supply pressure, or your room needs to be clean and dry. Clean air or nitrogen. Other noble gases or inert gases are sometimes used. You need to be cautious about using very small gases like helium, as those will be more likely to leak and potentially cause errors depending upon the instrument you're using. But the dry or nitrogen work very well. Combined air result in the system, cause damage. If the pressure sensor in your system is with liquid, it can still to other components, cause collision, cause to get clogged. So you're careful of leaks in the system, or excuse me, of any contamination from your supply pressure. Contamination we see is TFE tape. This is used on a NP pipe thread fitting. Fittings will seal on, so you'll need to put the tape on it to help in sealing. And that gets cut off and will get clogged into the system and perhaps clog up a valve. Directions. The amount of PTFE tape that you use, you wrap it multiple times. That's not to help any. That just increases the chance that you have that it'll get in the system. The 2 wraps are necessary, and that's it. With fitting, make sure you're wrapping in the proper direction. And first thread blank, because that first thread is what gets off when you're putting the thread into the system, and part that will get clogged into valves and so forth. So make sure that you back off one thread and leave the first thread empty, blank. And for the most common source of serious contamination, cause damage to your controller, repair bills, or contaminate the next unit that you're testing, is coming from the unit under test. You get items coming in from the field to calibrate something that had liquid in it, the environment where so it'll have liquids or particles, and those liquids and particles find their way back into your pressure controller. This is serious damage to your instrument. And time for your lab is you have to collect all the contamination and make sure that you didn't contaminate this device that's compatible with that first contamination. there to reduce this challenge, depending upon the different pressure controllers that you're using. Each of them have different levels of capability. I'm going to cover one that is a relatively new product from Calibration that can assist with that. What we call the Contamination Prevention System. Here, it's that gray test stand that has the gauge connected to the top of it. And what this is, it's available with the 6270A. It only works with the 6270A. And it protects the controller from contamination coming from the device test. And in multiple methods. When you use your controller, gas from your supply, or when you go up in pressure, the gas is coming from your supply into your controller from device under test. When you're going in pressure, the media is flowing from the device under test back to the controller and out the exhaust valve. A downward excursion is where you run into problems, where contamination from the device test or the unit under test gets back into your pressure controller. What our contamination prevention system does is have unidirectional flow. Going up works exactly the same. Pressure comes from the supply bottle into the controller to the test. When you're going pressure, you're going to test out the valve in the contamination prevention system. And downward excursion, the media back into the pressure controller. When you close that point, where there's relatively little flow between the controller and this under test, then the controller for doing the actual fine control, but point flow between the two. And gravity trap, where the contamination has to go down under test into this gravity trap and then back up in order to go through the system. And that trap includes a self-purging system where when you vent the controller, a second valve in the CPS that pulls whatever trapped in the gravity trap in the waste bottle. We also have a filtering system. Is a third level of protection. It's a two-stage filter, both a filtered filter and a custom filter. With that setup, it's important that you have a leak-free system, and you allow for stabilization at the set point to ensure that a pressure throughout the system. This acts as a test stand. As you see here, it's got the test connection on the top, where you can then connect your dynamic test, be it a gauge, transmitter, or so forth. Talked about the different considerations in the mechanical setup and the physical layout. Let's look at a couple of different software considerations. Control settings and capabilities. They can be at a time. Let's how some of those affect your performance, and then you should use what as your setting. Measures will have two different control methods. We refer to as a static and dynamic. Control. The control is always trying to get the pressure as stable as it possibly can. It is close to the set point as it can. So target pressure, the pressure increases to the target. First rate, as it gets closer to the target, it's going to slow down. As the pressure is possible to that target pressure, the controller will be continuously making changes, either letting gas in or letting gas out to keep pressure as close to the target pressure as possible. Close is oftentimes referred to as the control precision or the control performance, and then your ready tolerance. You'll be looking at a stable pressure that's considered ready and take your reading. Static control works differently. Once again, it's going to target that rate change decreases, and it'll control to just a bit above the target. At that point, pressure stops. Basically, it shuts the valve, and the pressure a closed system. Okay. Pressure to gradually decrease. Once there's some limit away from the target pressure, it can go on. It controls up to a bit above target, where again, and the pressure decreases. Now, why would one use the static versus dynamic? Why would you use static or why would you use dynamic? For the most part, in most situations, provide a much more stable pressure, and is preferred method by most. Based on it, I would say 90% or higher of all users of pressure controllers are in dynamic pressure control mode. Can eliminate when using a pressure controller and making sure that you have a stable pressure. Works in that option of it has a closed system. One, remember that pressure is affected by volume, temperature, and number of molecules. We have a closed system. You can say, okay, the number of molecules are the same. Changes in pressure are caused by changes in volume or changes in temperature. Some changes in volume and your piping expanding and so forth on pressure, but the majority of your pressure are going to be by changes in temperature. And that's really kind of what you see here is that as you go up in pressure, temperature with it. When you're going up in pressure, temperature, and as it decreases, the pressure is going to drop along with it. At that point for a while, your temperature will stabilize, and your pressure will naturally stabilize as well. A stable pressure for your measurement, but it'll take a little bit longer than it will with dynamic control. Is that if you have a leak in your system, all of this out the window, and pressure gradually decreases, you may pressure increases, which kind of a leak in your system and we're in unstable pressure. The pressure is stable and ready. Ask customers this question or users this question, they'll say, well, when you tell us it is, if the light on the front of the panel says ready, take my measurement. Well, how do we determine that the ready light comes on? How that the pressure is stable? See stability limit. And so for static control mode, we're looking, is it within the control limit? And is the change in pressure sufficiently small enough? And the dynamic pressure control, we'll be looking at the ready tolerance. Is it within the amount from the setting? These are settings that you can change in the instrument. The values when leaving the factory. Many times those will be very close to the overall performance, or the best performance instrument. You need to write for your application. Maybe you don't require as stable of a pressure for your calibration. You're waiting too long. You're waiting for something to stabilize when you don't need to. Very good setting is also resolution. The pressure on the front panel, if it's at resolution, it'll seem like the pressure is never stable. Looking at digits that happening on your actual calibration, on your actual application. So make sure you've got the resolution set properly for the application for the calibration you're performing. You have the option of changing is the how fast it controls pressure. Many people are looking is like, okay, I want that as fast as I possibly can so I can get more calibrations done. But what you may find is that slow and steady sometimes wins the race. You go further, you result in more overshoot and longer to stabilize at the pressure, where a decent pressure, reasonable pressure when you get the point, which makes a slower increase in pressure results in less temperature effects. So sometimes wins the race. Now I say slow, I'm not saying 5 point, saying 30, 45 seconds to set point. So relative and much quicker than doing using a main setup where you're controlling the pressure with a needle valve or pump with a hand pump. There's a you can do to improve the efficiency of your usage. Step size. Test with set pressure steps. It's a pretty common thing to do. Say that you want to do 20% steps up and down, or 10% steps, or 25% steps. The pressure from Fluke will have a step size. Step size equal to the pressure step that you want to do. Then you can go to each set point with a simple screen press on 6278 or button press on like the 7250, where say you're doing 100 psi gauge and you're doing 20 psi steps. You're 20 psi to go to 40 psi. You just hit the up arrow and it controls up to the next set point. And it'll do calibrations without necessarily having to set up a fully defined test, a pre-programmed setup using remote software, but step through the set points very quickly. Also have a pressure jogging feature. On controllers, the low pressure pneumatic controllers available from Fluke Calibration is normally handled through a jog wheel. So it's a rotary knob that you'll find on the front of the instrument. What you do is make small adjustments to the pressure, which is when you're calibrating things like analog gauges. So you want to control up to a nominal set point. Small adjustment to the pressure. So the under test is on it is pointing to the cardinal point. And to do, use the jog wheel to make a slight change to the control point, with a slight change to the actual pressure, and allow for an easy calibration. Found that actually putting a manual variable volume also works, but with the latest controllers that are available, they can replicate the same behavior without cost complexity of the component. The message out of your pressure controller, if ever possible, automation. You can hook everything at the start of your calibration, define one, hit go, and then walk away. Go drop a coffee or another calibration. Pretty much work done. Through remote interfaces. The most common are things like RS-232, EEE48, or USB. Controller to be connected to a computer. You do that through things LabVIEW or Compass for pressure software that's available from Fluke Calibration, or your own software if that's more a desire. With that said, you can fully automate the usage. Not the usage more efficient in that you stand there and watch it, you can move on to other work, but it also readability in the experiment. The same thing every time. How you train your operator, their variability in it, where the automated setup will get the same calibration every time. considerations when it comes to the calibration of these devices. First interval is 1 year. So the pressure controller with onboard sensor will need to be calibrated as well. So the calibration common interval for that is a 1 year interval, depending upon your application. Is like dead weights or piston gauges. Measurability can be a very large part of overall measurement uncertainty of the device. May sometimes be reduced by shifting the calibration interval. So, 0.075% of reading per year. If you calibrate it every 6 months or every 3 months, then that allowance for drift can also be reduced with it. Conversely, the cost can be reduced by increasing the interval when larger uncertainties are acceptable. So, if your device, perhaps it was purchased for one application, it's now being used for another, or proven to be more stable than what you considered when you purchased it, you can increase calibration interval and have an acceptable measurement uncertainty for your application, and reduce the cost of ownership, make it better to use. There is risk, obviously, in that if something does go bump in the night, there's more things that have been calibrated with the device since its last calibration. So your calibration interval, you need to set appropriate for your application. The most common is 1 year, but it may result in better uncertainty. A longer interval can result in lower cost ownership. So, regarding calibration, many found that a deadweight tester can make a useful check standard. The measurement uncertainty of the deadweight tester may not be sufficient to actually calibrate the pressure controller. But the deadweight tester provides a repeatable pressure that's very stable when used at the same location under the same conditions over a long period of time. Have a pneumatic deadweight tester next to your pneumatic pressure controller. Only say generate the full scale of your pressure controller on your deadweight tester. Over you can observe the span drift of the controller as to the deadweight tester. Now, when you do the full uncertainty analysis on the deadweight tester, it may not be sufficient to actually perform the calibration. Pressure over time is going to be very stable. So changes in that over time, just by putting the same exact weights on it, you can get of your pressure controller. Ability of your pressure controller. When make sure that you have the appropriate calibration standards for the low pressure, for example, in the water and so forth, the low differential pressure, something like the 4-ounce piston gauge, the FPG 8601. For ranges, higher pressure ranges, the piston is common. For C pressure controllers, you may be able to get away with calibrating against another pressure controller. Find that the majority of these calibrations are going to be done against a piston gauge. So, whether calibrating it yourself or sending it out for calibration, that's the equipment that you're looking for from your accredited calibration provider, such calibration. Also, the invitation is properly packaged for shipment. To damage in shipment if they're not packed properly, but just make sure it is properly packaged for shipment, or the best case scenario is calibrated in place, where you have to send it out for calibration. This having your own pressure standard like a piston gauge, by having someone like Fluke Calibration come in and calibrate it at your facility. Those stations may only be viable in certain situations where the economics make sense. So many people are going to send it in for calibration. So do so. Make sure it's properly packaged for this event. But pressure controllers, do consider that there are other options, either calibrating it yourself with your own reference standards, or having come in and calibrate it at your facility. About some of the benefits of a new controller versus old or round. We're all older equipment. Some age, including pressure controllers. Things like the quartz board-on tube that's used in the 7250 is known to get more stable with time and end up with better measurability as it gets older. But I think it's better with time. The components that are inside of pressure controllers, like and so forth, can provide numerous benefits over aged equipment or equipment. Provide better ease of use, stability. Newer devices have touchscreen displays, color displays that makes it easier to understand what's going on, how to set the different settings in the controller, and easier to use. It can be robust, especially as devices get to the end of their life cycle, can start wearing out, and easier to maintain. You get parts for things like a modular design, like what's found in the 6278. Have different options on maintaining the instrument. You can down modules so that you always you have no downtime, and that the overall maintainability of the instrument better. One to get the best of both worlds is older equipment where the key can be used in new equipment. Of that, with, for example, the PPC4 or the 6270A, we in older devices that quartz reference pressure transducer, use those components in either a PPC4 or 6270A, the best level of both worlds. Very efficient tools for calibration, proper maintenance, configure up, years of success. So this is open to questions.
Our first question is asking if compressed air can be used to supply pressure control.
Yeah, giant caveat. If you use, say, an industrial compressor, no sort of dryer or filter on it, you end up with liquid contaminants in the gas and cause damage to your pressure controller. So if you think about it from a overall standpoint, gas that's used in the controller at some point was compressed. 3,000 psi nitrogen doesn't exactly occur, so it was compressed at some point, be properly dried and properly filled to be in a pressure controller. And most of your controllers in their user manual will provide specifications on how clean and dry the air needs to be. And you end up with dryers and filters that are available on the market. Well, if you're talking to a supplier of gas bottles provide those specifications will allow to make sure that they're providing you the right supply gas.
Before I share the next question, just a reminder to everyone, please use the chat or the Q&A features to submit your questions. The second question, using a nitrogen tank, does the purity of the nitrogen, using a nitrogen tank to supply the controller?
The highest purity is a bit of something else. That's okay as long as, depending upon what the something else is. Many controllers will, with if it's moisture or hydrocarbons or pools that are in the nitrogen. Again, the use of each controller will specify what's required with the supply pressure, and it will provide guidance on the nitrogen that you have in your tank. Most of them is going to be what's often referred to as instrument grade nitrogen.
We don't see any other questions. We will leave the line open for a couple more minutes. If you have any questions, please do type them in or send your email questions to Tim. You see his email address on screen, tim.francis@flukecal.com. Also, we will be following up in the next, over the next week. We will be following up with an email with a copy of the materials presented today.
That email, assuming that the recording went, will include a recording of this webinar as well. This question is, does the Fluke compass for pressure allow for calibration of a DD or device under test using an averaging feature because of differing readings? Yes. So you can decide to over a period of time or average a number of readings from the device under test in case of situations where you have different read rates on your controller or your device test. Capability is also always recommended. Make sure that you allow stabilize before taking readings. Situations where the device under test receive pressure slower than other one, so you have everything stabilized before you take your readings. And again, if using software, it's always best to take full readings and average.
We will we'll be closing the presentation now, or the webinar event now. Thank you for joining us. Again, we will be sending out copies of the presentation and a link to the recording. If you have any additional follow-up questions or would like to talk to someone, please send an email to Tim. His email address is on the screen, tim.francis@flukecal.com, or reach out to us at flukecal.com. Thank you.